So today we begin the second module of this course. And in this module, we'll be primarily be covering the different network technologies, the communication technologies for IoT, which involves discussion about the different protocols which are used at different layers. Okay, so this lecture and the initial part of the next lecture, we will cover the infrastructure and service discovery protocols. So I'll talk about each one of them gradually as we proceed. Well, so far in the course, we have had an idea about the basic components of an IoT, the entire big picture view of the IoT ecosystem. And we saw that it's nothing but connectivity of different devices, right? The devices can be the ones which want to capture data, or the devices can be the ones which are responsible for transferring data, or it can be devices which want to process something on the data. So based on this requirement, we said that we can have some low-end devices, which we called the objects, or we call the things. And then supporting that is some network layer, which also involves some devices such as gateways, routers, which transfer this to a more resourceful system, making use of, again, the already established infrastructure called internet. And that takes us to more data computing or data intensive systems such as servers, cloud, where we can perform all the data analytics and data processing. So in the entire idea about building an IoT ecosystem, we saw that at different stages, we require connectivity, right? So here is a connectivity of objects to internet. We have connectivity of resourceful devices to either the objects or via the internet to other network devices. So it involves a lot of connectivity, right? And this connectivity between the different devices, whether it is IoT devices or the IoT devices connecting to the outside world, that dictates our network architecture. So in this lecture and the next one, we are going to basically talk about this part, that how the devices are connected among themselves, or the devices get connected to the outside world. So we are going to talk about the network architecture. And when we say network architecture, it actually involves the devices that are responsible for helping us in building this communication, as well as the different protocols, the different rules that we have. Now, the problem with this IoT ecosystem is that there is no specific architecture as such, right? So all the architectures that we have been talking about, or you will find mentioning across different resources, that's a perceived architecture. There's no standardized architecture as such as of today. The reason is that this particular system has been built using different kinds of devices. The devices, the objects, the things that we use are all non-standardized. Everyone uses a particular device depending on his or her requirement. So there is no specific rule as such to connect a particular device to another. You have, if you want to go for connecting two devices, A and B, you have to know how are they, what are the kind of connection they are using, and accordingly you design your system. So because of this heterogeneity, there is no specific standardized architecture. When I say architecture, I actually mean communication architecture. Now, for connectivity of different computers, we already have a specific architecture, such as an OSI model, or you can say an alternative to that is the reduced TCP/IP model. So this layered architecture is already in place for connection among different computers. We already know the different 7-layer protocols, the 5-layer protocols, and every layer has a specific role. It's already defined. So if you want to build a network, and that is exactly on which our network of computers or the internet is built, it's already a well-established 5-layer or 7-layer protocol structure. But that is not the case in case of IoT, because the devices are many, there are different kinds, absolutely heterogeneous network, and there are a specific computation and constraints which are there. The devices are, many of the devices are resource constrained, they are low power, low memory. So you cannot have that specific kind of architecture. And the problem is that these applications which are built for IoT are very, very specific. They are problem specific. So the requirements or the network requirements catering to these applications are also very, very specific. So we still do not have an network architecture. Okay. But to ease things, people have tried to provide a layered architecture in the same lines as an OSI or TCP/IP model. And that is exactly what we have been seeing so far. Either a 3-layer or 4-layer or 5-layer, but there is no standardized architecture as such. Well, whatever be the case, so the choice of communication technology dictates IoT device hardware requirement and cost. And this is the reason why, because you have to be, these are all related. What kind of an IoT device you are going to use often decides what kind of a communication technology you are going to prefer, or it is the other way around. You first decide on, okay, maybe I will be using a low power network, such as a Bluetooth or 6LoWPAN. So based on that, you start searching for the devices that support these communication. Okay, so whether it is a communication technology or the IoT device hardware, it all is dictated by the application. You start from what kind of an application are you trying to build. That will have its own requirement for what amount of what purpose, what is the area to which this particular IoT based system will cater to, what kind of an environment is it, and depending on that you decide the communication technology. So if it is a battery operated device, obviously you cannot have a very high end communication system. You need to use low power communication. And the moment you go into low power communication, which is the case of majority of devices, you automatically fix your IoT hardware. Okay. So if you say that, okay, I will be using Bluetooth, automatically you will search for a device that supports Bluetooth protocol. So you need a device that has a Bluetooth hardware. If you decide that, okay, I will be using some kind of a Wi-Fi, you need to search for a device which will support the Wi-Fi. So it should have either an onboard Wi-Fi or some kind of a Wi-Fi module you need to attach to. So that is what we mean here, that your communication technology, to which range are you going to communicate? What kind of a communication are you going to prefer? Will dictate what device you're going to choose. And obviously that has an economical point of view, that it decides what should be the cost. Okay, because when you are going to build your system, it will have an economics associated with that. It will have a cost because you want to sell it to the market. Now, if you are going for a very high-end technology, it will involve a lot of devices and automatically the cost will increase. So depending on what system are you going to build, that will decide what kind of a device should we use, a more sophisticated one with a higher cost or a lower one with a minimal cost. Okay, then we have, so just keep in mind one by one, why do we need to understand the network layer so important? Why is it so important, and why should we spend time in understanding this? Because that itself has a, it decides what kind of a device you're going to choose. Then there are a number of applications of IoT enabled devices, right? So a single networking paradigm may not be suitable because you may have multiple applications, right? So for that, you require many kind of services. So one single networking technique may not solve all your problems. So you have to use different kinds of network. The moment you start bringing in many different kind of networking techniques, automatically you have a more challenging problem because it not only increases the requirement of hardware, it also gives you how to integrate all that. So that's a big challenge. Okay, so all this has to be taken care of when you think about the networking part. And finally, the complexity of the networks. Now, because we are talking about different kinds of devices, it's not that all are same kind of homogeneous connections such as connectivity of computers. No, here we have devices which are of different types, different form, different data rate, different power requirement. So it's a heterogeneous connectivity of devices. And if that is so, there is bound to be some kind of interference. Okay, there will be some kind of interference among the devices. So the network should be robust and it should be sufficient enough to handle these problems of heterogeneity, problems of non-standardization. There is no standards as such. There is no uh, one device works using one technology of communication, the other works with another one. Say there are two sensing units you have deployed. Both are giving you data, but one is giving you Bluetooth, the other one is using Bluetooth to communicate, and the second one is using maybe a Wi-Fi to communicate. You see, there are two different communication medium you are using or different protocols you are using to get the data from two different units. But the data is arriving at one single node, and there you are going to do some processing. Well, that's the challenge. How do you solve this problem? So these are some of the connectivity considerations that one has to keep in mind while building an IoT ecosystem. So these are the challenges that you face when you talk about communication, that, okay, how the device would communicate. Let's see how we're going to solve that. And if, this problem is a very challenging problem. So it cannot be solved using one single solution. You have to have a layered approach. And that is the reason why, because the problem is at every level and you have a lot of things involved. Small devices, large devices, low range connection, internet, which is a wide area connection. So because there's a lot of things involved in that, you have to tackle this heterogeneity problem at every level. And that is the reason why your network configuration should also have a layered approach. So let's look at how we can handle that. Well, so let's look at the network configuration in IoT. If you divide your entire IoT system into a layered structure, the most simplistic model, the layered model that you have is a three-layered model, where you have the devices at the lowest level. We call them things. Now, the things are the one that collect data, do some initial processing, and these things which form the bottom layer, the lowest layer, they either can be connected in a very limited, geographical region, which forms the local area connectivity. You have some nodes which are connected to each other. They can either have some local area connectivity. So this is what we call a LAN, or there can be multiple such LANs which together, okay, so this is another LAN, this is another LAN, and together they may form something called a wide area network, such as this, right? It may so happen. All of these can be sensors or sensor nodes, wireless sensor nodes, and all of them can be connected via some kind of a wireless communication method. They form a wide area network. Right, so your objects or smart objects, they either can be in a LAN or they can form a WAN, okay, whatever it is. We know that the idea of things is to do some basically data acquisition, some initial data processing, some security and management that you can add to that. Because if you want to do some kind of processing, you may require some security and management here. So this is the network connectivity. So when we are calling about, we are talking about the lower layer, we are actually interested in communication, which is in a very limited region. The devices are connected, the devices which are connected in LAN will be using all the LAN technologies, very low end, low power, and very near communication technologies. Or at max, you can go for a wide range. Maybe you are deploying sensors or you're building an IoT system for an entire building or for an entire campus. To that extent, you can do, but still, it is within a very limited geographical region. So if you are doing it for your own house, you may be okay with technologies which the LAN technologies, which are very low range, such as Bluetooth or infrared or whatever. If you are extending that for a building, you may go for maybe Bluetooth, maybe like using a Wi-Fi. So depending on to what extent geographical location you are trying to build this your IoT system. Okay. Well, so this is the lowest layer. Now on top of that, where you'll actually move or your data to, so you send your data finally to be stored and to be processed. And for that, you require the second layer, the devices, the different techniques, the protocols that help you in moving your data from this lower layer to the higher layers. And that is all about the network layer, all the devices and softwares that help you in doing that. Well, there is also some connectivity that is required. You may require some kind of a gateway device which acts as an aggregator that collects the data from all the things and then passes it on to the network infrastructure. Now, this network infrastructure is again well built in network infrastructure that we have, which has already established techniques and protocols. So here we can go for the more standard IPv4 or IPv6 techniques, where the usual internet-based services that we have. Okay, so I should, because it's already an established, so you can go for the internet-based services, based techniques. So the idea is that we have the network, which on one side will be connecting to the low-end devices, and on the other side, it will be connecting via this internet to a more sophisticated infrastructure, which is called the cloud. And there you perform all your applications, analytics, and whatever. So this is the three-layer architecture that we have. So as we see that in this three-layer, we have a lot of connectivity involved. Connectivity between things and network. Network means the network infrastructure. So how the things will be able to provide the data? You have to talk about this side, okay? And you will also be talking about this side, the one that actually gets connected to the internet, or maybe this one as well, to the cloud. So we'll talk about each one of them. Today, we will be focusing on here, this part. So before we move on, let's talk about some of the terminologies. We are already aware of that. Just a quick recap. So for LAN, we know that it's a local area network. It's primarily used for short range communication. You may connect it to the internet or you may not. So majority of your things or objects that you will be connecting will be using LAN. Okay, low range connection. Now, what are the key things about this low range connection is that these protocols that will be used for the LAN communication will be very low power, mainly okay with battery operated devices, when you can deploy these protocols and you can run these protocols on battery operated devices. and will be for short range communication. Okay, so but there are a few challenges. We'll talk about that. And even you can move to wide area network, we call that WAN, and where you are going to connect various network segments. Now you may require, you are trying to deploy a lot of sensors, for example, your weather monitoring system or forest fire detection system, so or even smart irrigation system. So you will be deploying different kinds of sensors, but these sensors will be some sensor nodes will be deployed at a particular place in the field, and other kind of sensor nodes will be deploying at other places in the field. And maybe that there has to be communication between these sensor networks. Okay, so that will be through WAN. So that is the reason why they're saying that, okay, you can have different network segments, which itself will be LAN, and then they will be using some internet to connect themselves to form a bigger network of networks called a WAN. So yeah, so that's about this. This is the one that we are going to use in our smart objects. Then we have node, which connects to other nodes via LAN or maybe connected to other nodes via WAN. So nodes can be anything. It can be objects, it can be gateways. Okay. Yeah, you have been hearing this term gateway. So what exactly is this gateway? Well, it's nothing but a router that connects your LAN to WAN. Okay, so it's like this, that you have a number of LAN connections here, your devices. This is one LAN, and then you have another LAN. Okay, so this is LAN 2, this is 1, and here is your internet. Now, sitting in between this is your gateway that connects that to the internet. Okay, so these will be sensor nodes deployed at a particular place. They will be forming their own network, or they will be standalone nodes. And this can also be standalone nodes, but these nodes do not directly connect to the internet. They connect it through a gateway. So this basically is a router that collects the data from this, gets the packets, and forwards it to the internet. Internet means it's a well-established connection which is there. You forward it, and then from then onwards, you use the usual the TCP/IP model to transfer your data to some other location. This is basically the role of gateway. It's a router that connects the LAN to the WAN and the internet, and it forwards the packets. Okay, primarily this. So it's also a computer, you can say, okay, which collects all the packets and forwards it to the internet. Now, in addition to that, we have something called proxy. Okay, and you also have been hearing this. So what exactly is this proxy thing? So let me talk about that, and then you may have heard about this term proxy in case of connectivity of computers, but proxy is also used here, and the idea is, now the main role of this proxy, as you see here, it's written, it performs active application layer functions between nodes and other entities. So you can say it's kind of a bridge. Okay, so it bridges different elements. Now I'll bridges different elements of the IoT system. What is it? It's basically a computer. That's all. So now what happens is, it's now let me put it in this way. It kind of, so this proxy thing is it like it's, as I told you, it's a bridge between the different elements. So many a times, from the client perspective, the one which will be using, let's say, some IoT device. So from here you can say, so the proxy, it actually bridges the services. Okay, you have the services which includes now like web services, okay, and IoT services. Now, as I told you that, I'll give you the meaning of that. So this proxy is like, as it is bridging these IoT elements. So on one side you have, and I'm talking about in terms of the customer. The customer would like to use some kind of an IoT service and will be making use of some web service to access that. So suppose I want to see some kind of a sensor data, right? And the sensor data is collected via the IoT device, and that data is available to me through an application which I will be using through an app. So I'm using a web service to monitor that, but the data is actually gathered from the device which is making use of some IoT services. So this proxy is something that bridges these two. Okay, so let me give you some idea about how it is done. Now, this itself provides you the services, right? So let's understand this way, that suppose many a times these IoT environments which involve these devices and all, they work in a resource constrained environment, right? Because they are more only battery operated devices, low power devices. So suppose there is some kind of an IoT device, or let's say a collection of IoT devices. These are all IoT devices. And these IoT devices are collecting some data and providing that to some application. And there is some customer which is looking at that application to see the data collected from these devices. The problem with these devices is that suppose if they have to send the data periodically, then because they are battery operated devices, they normally don't do that. They send the data. I mean, data means, let's say they are updating the status of that. They send the data and they sleep most of the time. I mean, these devices are primarily hibernating. So why? Because they save power in this way. So they send the data and then they go to sleep. That is, they hibernate. The power, um, the lot of computations are put in sleep so that power can be saved. Well, during this time, if there is some client that wants to update or see the updates of that particular data, how will that happen? So what happens is, now this is maintained through some kind of we can say here, some kind of a resource directory. Okay. So I maintain a directory, and there they update the data here, right? And this resource directory that I maintain here is kind of, it's a directory, right? So what happens is all the devices, let's say device 1, device 2, etc., they have to register themselves in this directory. So this is a registration process which is involved. And as you see, it's a resource directory. It maintains a list of how many resources are there in the system. And all the updates that are happening are actually happening here. So the device updates it here and then goes to sleep. So the good thing is that the application or the customer, if it wants to see, it doesn't, it just has to look up to this and you can get the information. So even if they are idle, I mean, they're sleeping, you don't have any problem because you are actually communicating to this. So this is some of the services, and this resource directory, okay, is actually facilitated through proxy. So this is one of the reasons where you see that proxy actually performs some active layer functions between the nodes, such as maintaining of resource directory of devices. Okay, so as I told you that though there is no as such any standardized protocol, or there is no standardized architecture for IoT, but okay, to some extent we have perceived that this is what we can think to be the layered architecture depending on the role played by each of the devices in building that entire system. So as it is the lowest layer, we called the perception layer, or we also call that the object layer. So this layer is the one that is having the physical objects, sensors, actuators, and whose main role is to gather the data. That is the basic idea. Okay, so this is about the last layer. We have discussed about that in the last 2 classes. Sitting on top of that is the network infrastructure, which we may also call it the object abstraction layer. So whose basic idea is data transmission, that how can you transmit the data that you have captured from the lower layer to the upper layers. And this, okay, so one of the requirements of this data gathering phase is that the sensors, actuators, whatever you have, they must be kind of a plug and play device, right? We have seen that how we use different kind of sensing elements, and they had their own interfaces, right? Like I2C, some used I2C, some were using some serial port or USB, but whatever it is, this data will be, they will be plug and play, so that you can use heterogeneous, right? You don't have to write a protocol for doing that. But we saw that. Now, the requirement for this data transmission is again that you are going to collect the data from these objects and you're going to transfer that. So by using some channels. So we are going to talk about the protocols here. So the idea is that you should have some kind of a functions that should help in transferring the data from the lower layer to the upper layer, and it should also have some kind of a facility to handle directly from this to this layer, that is the middle layer, okay, such as cloud computing and whatever. So this is about the second. We are going to detail about that. So for the timing, I'm not going into the details of this data transmission layer. We are going to spend the time basically on the protocols that help in handling both these layers. Now sitting on top of this is, we call it middleware, and or we can also call it the service management layer, whatever. So the service management layer is all about process information. Okay, so where you do some kind of a decision or you do some kind of an analytics. So what its basic role is, it pairs the services, okay, to its requester. So this is, so there is a service which is provided by the lower layers, and there is some service which is requested by some user through some app. So there can be a lot of services which are there. There are a lot of services which are available from the lower layers, and there can be a lot of requests. So it basically maps the request to its corresponding service, right? This is the role played by this middleware or the service management layer. What service am I using? Am I going to see the temperature, weather, humidity, pressure? What exactly do I want? And accordingly, based on the user requirement, it provides that service. So this is the management that you need to do. It's a mapping. And the good thing about that is it allows now the programmers, the IoT programmers, right? So it allows the programmers who are going to design this app, okay, to work on different objects, to work on objects. These objects are absolutely heterogeneous, and though they are heterogeneous, now irrespective of the platform, they can work on these objects. So that is the best thing that we have. It's kind of an abstraction that is created, and I am looking at that abstraction without going into the details or the underlying platform. So this is the basic the role played by this middleware layer or service management layer. And as you have already seen here, this layer is also involved in decision making, where you do some kind of an alert. So it involves this cloud and all, where you run, you keep the data, so the database, or you can run this, take some decision making. So this is the management layer. And sitting on top of that is the application layer, which is it provides diverse kind of services. Yes, because now as I told you that you have a different kind of application for the same kind of from the same IoT system, you may require different kind of applications. I may require, if I require the temperature monitoring, I will be having a different kind of a use case than if I am going to measure pressure or the pollution or the humidity. So depending on the use case, you will have different kind of applications, right? So this is the role played by, and that is the reason why we say that they are smart applications, because the applications are for a specific purpose, and accordingly your use case changes, right? Well, and sitting on top of that is the business layer, which is all about uh, system management, because there's an economics involved in that. And what you would like to do is that the data that you collect from here, you want to apply some business models, because until you make it profitable or interesting, you don't earn out of that. So that is the reason why you involve a lot of analytics here. The big data analytics can be used, and you design some business models so that you can have some informed decision making from the data you collect from this network layer. So the data collected from here is obtained and some decision making is performed. So this is the 5-layered architecture that we have for an IoT. I repeat, there is no standard architecture. This is a perceived concept, but depending on the role played or the different requirements, we can argue that, okay, this can be a layered architecture. Well, because there are a lot of connectivity and a lot of data transmission involved, we can divide the protocols, the network protocols which are used in this 5 layers into 3 categories. We can club together this data transmission, the network layer and the perception layer, the object or the object abstraction layer, and all the protocols that are involved in this part, that is connection between the device and the network, or the network and the middleware, they will be called infrastructure protocols, because they are actually related to the infrastructure that is used for building this IoT. So what are the protocols which will actually involve device to device communication? Then sitting on top of that will be the service discovery, which will be more of the protocols ensuring the middleware layer, okay, the service management layer. So because there are protocols that will provide you some kind of a service, we will be calling them as service discovery protocols. And finally, we'll talk about the protocols that help us in building the different applications, the different IoT applications, and we'll call them as application protocols. So primarily, we have three class of protocols when we talk about IoT. The infrastructure protocols that deal with the lower layers, the service discovery protocols that are involved in the service management, and finally the protocols for building applications for IoT. So we'll see in this lecture only the infrastructure protocols. In the next lecture, we'll talk about service discovery and application protocols. Let's quickly have a view of the different protocols that we have, and we'll be covering them in our course. So I will, for the time being, not talk about this. So if we look at the lower layer, which is the physical layer, so physical layer, data link layer, and we call it data link layer, or the object abstraction layer, whatever you call it. So these two, we will primarily be focusing on these three, right? So we have a standard called IEEE 802.15.4. This is the standard that we are using. This is the protocol that we'll be using for communication between devices or devices to gateway. So this is at the lower layer, where we will be interested in how to transfer the data bits. Okay, so that is the protocol that we are going to use. We'll also be looking at the EPC Global, which is about the RFID devices, where we have a device that is tagged to a particular object, and that will transmit the data through some antenna and will be captured by a receiver. So this will be, again, a very lower level protocol that we are going to talk about. And then we have the LTE, which is the data communication that we usually find in our mobile phones. So this will be the three kind of physical layer protocols that we are going to talk about: the LTE, the IEEE 802.15.4, and the EPC Global. Now, sitting on top of that is the data link layer, which will ensure the data correction, that is, the data is transmitted properly without any errors and all, error correction and all. So this protocol will take care of the error checking, etc. And then comes the adaptation layer. So we have discussed about 5 layers. When okay, the network, and I cover adaptation and data link together. So that is what we were calling as the middle layer, the object abstraction layer. And adaptation, in a sense that you see on one side you have the low-end protocols such as this, and on the other side you have the high-end protocols, which involves a proper IPv4 or IPv6 communication. That is already a standardized way to send the data. There's a specific packet format that this will be the packet size, this will be the data in the packet, the header will be this. So there's already an established format for sending the data. But on the other side, on the lower side, when the devices are giving you the data, they are giving you through different kind of low-end protocols, right? So there has to be some kind of an adaptation so that the data can be transferred. That is the reason why we are going to see some adaptation protocols, and one of them is we have a 6LoWPAN that takes care of that, because it is actually IPv6 over PAN. And it's a very challenging thing because there are two different kind of protocols you're trying to mix. On one side you have IPv4 and IPv6 that is actually followed in the internet. On the other side you have low-end protocols. So you're trying to mix the two. It's a very challenging problem. So you need to design something so that that can be handled. And that is the reason why we have 6LoWPAN. So it's basically IPv6 over a low personal area network. So how can you integrate that? That is the reason why this was there. And this is kind of an adaptation layer. So together they form this infrastructure protocols. And then we also have protocols, which the routing protocols, we call them RPL. So this actually falls in the infrastructure protocol as well as in the network layer, because it's all about how do you route the data from, let's say, the gateway to the cloud or to some other server. So this is the routing protocol. Or maybe how do you route the data from one device to the other. So we'll talk about that. So totally we see that we have routing protocols, RPL, we have some kind of an adaptation protocols like 6LoWPAN, we have some data link layer and physical layer protocols like IEEE 802.15.4, EPC Global, and LTE. So in this lecture, we'll be focusing on this part. Sitting on top of that are some service discovery protocols like MDNS, DNS-SD, which are also part of the network layer, but they are more of service discovery protocols. And then we have a few application protocols we will be covering in depth. CoAP, the constraint application protocol. We have the MQTT, which is the message queue telemetry protocol. Very on the most two popular protocols for handling IoT devices. We'll actually have a tutorial and lab session on this as well. And then we'll also be talking about the HTTP protocol. That is the standard way to transfer text and data from one computer to the other. But in this case, how can we trim it down or bring it so that reduce it so that it can be used in IoT environment. And we'll have a specific notion about this HTTP, which we call the REST. And you may have heard of this term, REST APIs. So we will talk about the REST-based data transfer. So overall, this is, and we have AMQ, DDS. So mainly we'll be focusing on these, the ones that I have marked here. Okay, so keep in mind these protocols, where do they lie in this network stack, and what are they mainly used for? So let us begin with the infrastructure protocols. So the first thing that comes to our mind while having infrastructure protocol is that it involves devices and applications. It involves devices and the network infrastructure. So primary among them is the routing protocol. And as you see, The idea of routing protocol is to develop a protocol that will be able to send the data packets. Just go back to the previous slide and you see RPL actually is an infrastructure protocol that handles the network layer. So its job is basically to obtain the data from the devices or things and then pass it on to the higher layers. Okay, the router which will actually be putting it into the internet. So how are you going to design that? Well, the data that is going to be sent is an IPv6 packet, the one that will be transferred. Okay, now I will come to why IPv6 was required and all. So it's Internet Protocol version 6. It's a way of addressing your devices. So you may have an idea through your networking classes that whenever you are going to use devices using an internet, it has to be addressed, right? Because if there's say some node N1, if it is going to get connected to node N2, now it has to go through this entire infrastructure, which will be having some other nodes or then the internet, and then finally it will reach here. Well, for that, it has to be identified, and this will have an address. So it must have an address so that this can be identified in this entire network. And we know that there's a standard way to address that. We are using the IPv4 addressing scheme, 32-bit, and we are using this IP addresses to identify a particular node. But the problem with the devices is that there are so many devices that very soon you will run out of the amount of addressing range. So then we shifted to IPv6, which is again a 128-bit addressing scheme, and that is sufficient to cover all the devices that you like to connect to the internet. So the problem is that this particular IPv6 packet, the data will be sent in the form of packet that has to be routed through a low power and a lossy network. This is the problem. Why? Because the network that you are going to build using these devices, right? These devices, the one that you are going to build, if you are going to build this connection, now this is making use of devices which are very, very error prone. They are limited in processing power, right? They are battery operated, very low memory. So there is every chance that there can be a very low data rate. It can have the low packet delivery rate. Packet will be delivered with a high latency. You will have a high packet drop rate. Packets will be dropped in the process. So these are some of the problems that can happen. So your routing protocol should be robust enough to handle this problem. Okay, where are these networks that there can be wireless personal area networks? You have some devices which are connected, or it can be wireless sensor networks. You have all these sensor nodes. So this is basically, let's say, a WSN. All these are sensor nodes or sensing units that themselves have created a network. But the problem is all these sensor nodes are all battery operated, and you know that they are only limited power. So if they want to transfer some data from here to here, there's a chance that the packets can drop. So this is a very unstable, unreliable network. How can you do that? These kind of networks that we are talking about, now they have a capability to optimize and save energy. We know that, as I told you, that majority of them, what happens is they don't keep on sending data, because if they do, then they will drain out the battery. They send the data and then they sleep. That is, they go into hibernation. That is one of the ways in which they optimize and save energy. Then they support traffic patterns other than unicast. It's not necessary that they only have unicast. Means you send from one to one. It's not like that. They can send at a time to many. Okay, it's a multicast. Or they can run the routing protocols over link layers with restricted frame sizes. So they can restrict the amount of frames that you're going to send. So these are some of the properties of such networks. So making use of that, can we build a more robust protocol so that we can handle these problems? Now, I hope you are able to understand the challenges that we have when we are dealing with IoT devices. Just because you have an internet and you have a device, okay, you just connect that device, or you have a collection of devices, you connect them, it doesn't work because there are a lot of challenges. It's not a computer that has a main supply, a lot of processing power, you can run very sophisticated networking protocols on them. No, it's not like that. So you have to think about the challenges and accordingly design the protocol. So the protocol, the infrastructure protocol that was has been designed or they're using is actually dependent on how good a topology you can design. So if you can design a robust topology, that is one of the requirement, or it can be one of the solutions to handle that problem. Why? Because if you have a robust topology, your idea is to have minimal routing. See, the idea is routing path, right? Routing from one node to the other. So if you can reduce the routing size or the routing path, then possibly you are saving a lot of power. So that you have to think that how can I design a topology so that I will be requiring minimal routing from my source to destination node, and I will be requiring there will be a dedicated path so that I can not have to search for a lot of things. So the routing algorithm will be simpler, and I can have I can increase the reliability and the performance. So this is the two requirement. And for that, you have to build a robust topology. So what the idea is, can we begin or can we design a protocol which is based on a distance vector, distance from one node to the other? Okay, how? One of the example that we are showing you here is this RPL topology, which is kind of a graph that you have built, and it is a directed acyclic graph, a DAG. Okay, I hope all of you are aware of this data structure, the directed acyclic graph. It actually connects nodes. From one node to the other, you have a link, but you don't have any cycles. Okay, so it's a directed graph from one node to the other as an acyclic. There is no cycle. And that is one of the constraints that we put, that if you are going to build a topology connecting different nodes that will be transferring data, do not put any cycle. That will solve a lot of problems. Now that supports multi-point to multi-point. Yes, that can be possible. Or you can have a single point to single point, or whatever kind of topology you want to cover. So let's look at that. Keep in mind, the idea is minimal routing, more reliability. And if this topology, does it work to solve our problem of data communication over a lossy network? Idea is distance vector. Let's look at the protocol. Okay, so what we have in this is we build a topology, and the topology that we build is a graph, and it's called a destination oriented directed acyclic graph, DODAG. Okay, what is it? It's a single rooted graph, and the root is your single destination. So you want all the data to be collected and send it to here. So you can just model this as a graph with a root, and this root can be, as you see here, this is a border router that actually gets connected to the external network, right? So this root is the one that will collect all the data coming from the lower layers, and it will collect the data and will send it to the external network. This is an internet. This is using the usual IPv6 network, but it is going to collect. So the router which is actually connecting to the internet is your root, and all the lower devices that will be collecting or providing the data will be the nodes. Okay, so they will be the node. So this is this. The interesting thing is that this graph that you have, it does not have any outgoing edges. Okay, so you have this, it's a directed acyclic graph. So you have the outgoing edges in a sense that, okay, so it's for this no outgoing edges in this last one. Sorry, for this root. Okay, so no outgoing edges of this root. So all the edges that come to the root are the incoming edges, and this will finally transfer to the external network. So that's not part of the graph. Okay, it's an interesting data structure, which is a combination of an instance. So you can have, these devices which are connected. You can have each one of them can be called an instance, and you can have an ID for each one of them. Okay. Now, in addition to this ID and instance, we can also have something called rank. And this rank is nothing but the level of the graph in which this particular node is. So as you see, they are ranked based on their individual position relative to the root, right? And rank, it increases downwards. So you see this is rank 0. These two are at the same level because they are directly connected to the root. So they are rank 1. I can also have a connection from here to here. So in that case, this fellow will have a rank 3 as well as a rank 1 because it gets directly connected to the root. So depending on the particular level in this graph, it will have a rank. So rank 1, these are rank 2 because they are transferring data to nodes which are at rank 1, which in turn transfers the data to the rank 0 node, which is the root. Okay. So in this way, you can build your graph. Correct? It's a destination oriented, directed acyclic graph. Okay. Now looking at this data structure, we see that the root is the border router. Now interesting that each node has information about the parent, only the parent. Look at this. It has information about the parent, right? But no information about the child because there is no, it collects information from it gets the data from this, but it doesn't know from where it is getting it. And it doesn't need to know. It actually has to pass on to its parent. So it needs to know to whom am I going to get that or send it. I don't need to know who is giving me. I'm just getting the data. Okay, so that information is, so it has no information about the child, but it has only information about the parent. So this makes this as the, I mean, this is about the root and the different nodes that we have. Let's see how the communication happens. Now, for this communication to take place using this DODAG, there are a few control messages, and we have 4 control messages that are used. The first control message is something called DIO, or DODAG information object. Now, it's an information that is initiated by the root. Okay, just think it in this way. This is the root. Now, the root has there are a lot of devices which are connected. Your idea is to build a path, right? Build a path for what? For a path so that a device can provide the data. To whom? Ultimately, the data is meant to be sent to the root node. So all the data basically should reach here. So the roots initiates the process by saying that, see, I am this node and here is my information. Now it broadcasts or sends this information. Look at this. Its DIO is the object. So what it has is, it is used to keep the current level of the node, but this DIO information is initiated by the root. Okay. And what it says is, well, I am this node. This is my location. So it broadcasts that. Okay. And for the rest of the nodes, which are just at the immediate lower levels than the root, they keep on broadcasting. But the good thing about this broadcasting is that from here, you are actually, mentioning that, okay, I am at this particular distance from the root. So when one will broadcast, it says that I am at the first level, I am at this distance from the root. So when it reaches to 3 knows, well, the 1 is at this distance from the root. Now 3 can have other nodes as well. It can have other other nodes that connect to 3 or send this data to 3. Then there is a check to be done that which is my parent, which will I take as my parent, right? So if that is the case, then I have to fix up a parent. Well, 3 decide that I will take 1 as my parent. The moment it decides that I will take 1 as my parent, now this path is established. It is from root 1, 3. So any data that you're going to be sending to the root will go from 3 to 1 and from 1 to node, 1 to root. So see, the path gets established. So what happens is you need this information to be broadcasted to the node, and during the process each node will be sending their information, and when it will be reaching, the node will decide, okay, which is my parent. So this is the information object that we are talking about. It is used to keep the current level of the node. It decides the distance of each node to the root based on some metrics. It can be distance, it can be some other performance parameter, and you choose the preferred path. That will decide you the path. Okay, this is the path that I take. So henceforth, if I'm going to send my data, I will be sending to this parent. That will decide its own parent in this way to the root. So the path gets established. Then you have a destination advertisement object, now which is used to unicast destination towards the selected parents of the node. So you see this is the DAO. It's in the reverse phase when you are actually sending the data. Okay, because all of the devices are basically meant to send the data to the aggregator, to the border router. So once the path is established, now you keep on sending the data. Now for every DAO that is sent to the upward, that is you help in the upward movement, you also will be sending an acknowledgement just to show that, okay, the data has been received. So it will come from the parent to the child once the path has been established. Okay, so this is the acknowledgement that we are talking about. In addition to that, there's an information solicitation, which is like there is some node which is not getting this DIO because it's not part of the path. It may request for some neighbor node which is along the same level and get the information from there. So that message is what we call the DIS. So there are 4 messages that we are going to use. Let's look at the process. Now this is how you will be building the DODAC. The root will first start sending the local information. It will take a DIO message and will be sending to all the levels. Look at this. This is the first, the switch is initiated. Now, as the root sends this to the client node, okay, whether it's for 1 and 2, for both it sends. It's like this routing information is being sent. Okay. Now, the routers that are present at each level, they will register the parent path. Okay, so they will get this information. So client 1 will say, okay, this is the root, and DIO message will have the information, the routing, the details about the root node. So it will maintain this in the client node and will forward that with its own information to the downward movement. So you have a next router, it sends it. So each node, it propagates its DIO message, and gradually this graph gets built. So a first step is propagation of the message, DIO message via different routers. Now, when a message comes to a router, it decides which is its preferred parent. And once it is defined, the parent is decided, automatically the path gets decided, path to the root that gets decided. So this is how basically you have your connection established. You see here, this is client node 3. That's not directly getting the DIO from the root. So what it does is it uses this DIS and it asks the DIS from the client node 2. So client node 2, once it gets, so it requests for the DIS, gets it from the client node 2, this DIO, and accordingly starts sending the data. So its parent becomes client node 2. So here is the link that gets established. So this is how you build a topology, which is called DODAC. Now, there can be 2 ways of routing when you are going to send this, it can be non-storing, and which is uses an IP source, means you know the source and you fix up the path, and your destination, your transfer will be via that, whether it is the downward movement of the traffic when the DIO message is coming, or it is the DIO message which is traveling up. So whatever it is, it can be a fixed path, or it can take help of an IPv6 addressing. Okay, depending on that, if it is IPv6 addressing type of routing messages towards the lower level, you call it storing. And non-storing is because you have fixed up the path, so there is no need for storing the information. So it's called non-storing. So is it okay? The idea of this, is it clear to everyone? The DODAG information, how is it being used, the RPL? Okay. The next protocol that we are talking about in this physical layer is IEEE 802.15.4. Okay. Now this is again a physical and media access control, and actually this was this started with as a sub layer for your the MAC protocol. Okay, so this was in fact not started for IoT. It was designed for a sub layer, okay, for your MAC, the media access control, and it was basically for low power PAN. So the idea was that for personal area network, which is built, if I can build a protocol for handling, at a minimum power or for low power communication. With this idea, this standard was developed, but as it started, when it was used for communication among different computers, and it started giving us a lot of benefits like low power, low data rate. And looking at these benefits, people started thinking that, okay, if it is so good for computer connection, for communication, can it be used for device to device communication? And with this, this was introduced into the IoT communication technology or the layers. So what it basically is, it's a communication protocol where its main job is to handle the physical and the media access control. I already told you that if you can look at, if you go back to the IoT protocol stack, the lower layer, we have the physical layer, which is actually the one that handles transmission of the data, the final, the lower end data, actually the bit pattern that has to be transferred. So, which handles the physical and the media access control. And this is the protocol that handles this. It's maintained by a working group, which is called the IEEE 802.15 working group. And this 802.15.4 is actually the basis of many protocols such as Zigbee and wireless HART. We are going to talk about this Zigbee in just a moment. So let's look at what exactly is the idea behind this. There are quite a few features here. It allows low cost, low speed, ubiquitous computing, can used in any application. The most interesting thing is that it is, okay, so it's low speed, so it's a low data rate. So even when we have, a system where you don't need to send data at a very high speed, it's safe to use this. You will typically used for wireless personal area networks. For these purpose, it is used. Power consumption is also minimized. That's a very, very handy thing to have, because we are going to use this in IoT devices which are battery operated, because there is a short packet transmission, and that is the reason why the power consumption is less. The advantages is very tolerant to noise. Okay, tolerant to interference and noise. So you can have a almost kind of a very high performing transmission. And the other advantage is that it uses, because we said that in IoT you have heterogeneity of devices, a lot of devices will be there. So there can be a possible collision when there will be data. When everyone is using the same channel, whether wired or wireless, there can be possibility of collision, but it allows the collision avoidance problem. So all seems to be good for this, and it allows multiplexing, so it allows multiple users to be there. So many nodes can be connected. So if you're using 802.15.4, many devices can be connected. It's a good thing about that, and interference free. Transmission is almost line of sight, and it works, good for range. Even outdoors, you have 1,000 meters, till 1,000 meters it can go, rarely, but okay. It uses number of topologies like star and mesh. So we'll talk about that just a moment. Let's see what are the physical and the MAC. What exactly is this protocol planning to do? So it's actually a interface. The physical layer of this 802.15.4 that handles the management. It maintains a database of information on different networks, and it provides a data transmission service. As you see here, that's what the role of the physical layer. And so all the physical layer, functionalities, such as dividing into frames or sending them, and what kind of whether it is going to use multiplexing, whether it is going to use collision avoidance, at what frequency will it be sending. All this is handled in this particular physical layer. The MAC layer is more of handling the integrity of if the transmission has to be done. It allows media access, number one, because it's MAC. So it allows media access. Then it allows error-free transmission. And it also allows some kind of a secure services. It guarantees time slots, frame validation. So these are basically done using these two. Okay. It actually it allows 3 data rates depending on the direct spectrum sequence. The 3 data rates are 250 kbps at 2.4 gigahertz, 40 kbps at 915 megahertz, and 20 kbps at. So you see, as the frequency drops, your data rate. So, but you can go as high as 250 kbps. It's okay for low range communication. Okay, not so high, but 250 kbps at least, for because you are not going to send too much of data. You're only going to send only some specific data, and also for a small range. So this data rate is okay. Okay, and this is at 2.4 gigahertz, so it's quite a high frequency. Okay, so what is and how this protocol works? The nodes that make use of this IEEE 802.15.4, they are of 2 types. They are either full functional devices or reduced function devices. Full functional devices are those which normally act as the coordinator. Now it's like this, that you create a group. Out of the group, one is a leader, and the others who are not so strong, they pass on the information to the leader, and the leader connects to other leaders or to other network. So it's like this. So you have a coordinator. The coordinator was the one that will be creating, controlling, and maintaining the network, as you see in this diagram. This is a personal area network where the black ones are representing the full functional device and the white ones are reduced function. Reduced function means they don't have so much amount of power, which are constrained resources. So you can think the PAN to be kind of a gateway, something of this, and these are the microcontrollers or the sensing units that you are connecting. So they are connecting it to the gateway, and from there onwards you connect it to the other network or to other clusters. So you have, if you remember when we were talking about the wireless sensor network, one of them was the coordinator, which was collecting from other sensor nodes, and then that was communicating. So you can also have a cluster tree, as you see on the right hand side. You have those clusters where the red ones are the coordinator. The white is the coordinator, the red one is the pan coordinator. So this fellow is coordinating between these two green ones. So you have local coordinators, which are the the local pan which are getting connected. This is one, this is one, this is one, this is one, and each is having a coordinator. The coordinators are connecting to the pan coordinator, which is the cluster head. And together these 1, 2, 3, 4, 5 pans, they form one cluster. And one cluster has a cluster head. So in this way, you can have the connections. So this is again one kind of a topology that we can have. And so based on that, we have a protocol which is called Zigbee. Now, the lower layers of IEEE 802.15.4, the lower layers are handling the physical and the MAC layer. It normally does not follow or does not allow or does not talk about the upper layers. So this part is not normally handled by this. So people thought that, okay, if we can build some application layers on top of this already established IEEE 802.15.4, and that is what gave rise to something called Zigbee. So the Zigbee protocol, it actually uses this standard for the physical and the MAC layer. And the network and the application layer is built on top of that. So what we have is two bands. We have 816, 915 megahertz, and data rate is about 20 to 40 kbps. Well, that's already we decided. We said that it's around, because it's using IEEE 802.15.4. So the kbps, the data rate will be same. Maximum number of nodes is 1024 that you can have in a Zigbee network, and range is 200 meter. It also allows some kind of a security feature, that is, it allows 128-bit 8 AES encryption. And the end devices, that is the reduced functional devices, we just saw the other two kind of nodes. The reduced function devices, they can go into sleep mode to save battery, and the connection will only be between the coordinators. So the rest of the devices which are collecting the data, were low end ones, they don't have to keep on, turn on they don't have to be in active mode for all the time. They can be hibernating. This is the structure of the Zigbee network. The Zigbee network, as you see here, is we have shown the star mesh and the cluster tree. And you see there's a coordinator, there's a router, and an end device. So the blue ones are the routers, the red is the coordinator, and then the end devices. So the end devices are connecting to the router, and the routers are connecting to the end device, to the coordinator. Okay, so this is the topology. So how does it begin? The coordinator is the first one to be installed. So if you want to build a Zigbee network, you first have to install a coordinator, and that will in turn start other Zigbee components. It selects the channel and it gives an ID to this pan. So this will have one ID, this will have another ID. So it gives an ID to each one of those personal area networks. And then the router joins in, and gradually the end devices. So in this way, you gradually build the Zigbee network. Okay, so yeah, so I will finish off this and maybe we can stop it here and today, and I can take up the next class. That is on Friday, we'll be taking up the okay. So for the rest of the lectures, for the rest of this infrastructure protocol and service discovery protocol, we'll be covering that in the next lecture. And once we cover this, we'll then move on to discussion about the application layer protocols. Okay, so we'll meet in the next class.